In this video, we're going to take a look at how to deal with the case of having a 0 in the first column. And so notice in the header here I've specified the 0 is only in the first column. And so the reason I've done that is to distinguish from a case we're going to consider later where we're going to have an entire row of zeros. So even just for a 0 in the first column, that's going to be an issue because what it means is if we're using that general equation to populate the rows below where the 0 is in our first column, we're then going to be dividing by 0, which is not something that's good to do. So we're going to look at two ways we can get around this. So sort of two methods for solving this case of a 0 in the first column. The first one we're going to look at in this video, and it's called the Epsilon method. And the second one we're going to come back to in the next video, and that's going to be the reverse coefficients method. All right, so reverse coefficients. Okay, so let's start by just defining what this first method is, our Epsilon method. And then once we sort of know what we're trying to do, then we're going to take a look at an example and see how we can actually apply this. So our Epsilon method, basically we're just going to replace that 0 with an epsilon, and then we're going to let that epsilon be a really small value. And so we have sort of two things to choose from. We can let it be a really small positive value or a really small negative value. And what we're going to show is that it doesn't matter which one you choose. So we're replacing that 0 with our Greek epsilon and letting epsilon go to 0. And so that can be going from either the positive side or the negative side. So basically we can be going to 0 plus, or we could be going to 0 minus. Okay, so again, I think this is going to be a lot clearer what our issues are, how we get around it if we look at an example. So let's say we want to find the stability of some transfer function. So we want to find or determine if a system is stable. And so let's take a look at some equivalent transfer function, t of s. And so instead of find, I should really say determine stability. So we're determining whether or not the system is stable. We're not designing for stability in this case. So as always, what we're going to do is create our Routh table when we're investigating stability. And we're not really concerned with the numerator, so we're going to focus on that denominator. We see it's a fifth order. And so because we have a fifth order polynomial, that means we're going to have 5 poles. And so we'll come back to that later. Our highest order then is our s to the 5th. So to be consistent with how I've been doing this before, let's go ahead and use blue for sort of our initial information. So we're going to label our rows s to the 5th, s to the 4th, s cubed, s squared, s to the first power, and s to the 0th power. And now remember, as we're filling in our Routh table, we're going to look at our highest order coefficient and then skip every other one. So we get those numbers for our first row. So we have 1, 3, and 5. And then for our second row, we're going to come back to the values that we skipped. So 2, 6, and 3. Okay, so now what we can do is we can populate our Routh table like we have been doing before. And so again, we can put our bars over here if we need to, if that's helpful for you, to sort of keep that in line. And so what we see if we're trying to find this component there, remember we're going to have a matrix. This is going to be our first column. This is going to be our second column. So we're going to have something that looks like this. So that entry, so let me just call this B1 as a placeholder right now. So B1 is going to equal negative 1, 2, 3, 6 divided by, positive 2. Okay, so of course we can see here we're going to have 1 times 6 minus 2 times 3, which is going to give us a 0. And so the problem would be then if we come to calculate C1, instead of a 2 here, we're going to have a 0, and that's where we don't want to be dividing by 0. So what we're going to do is we say, all right, this B1 gives us a 0. The first thing we're going to want to do is we can look at B2. So we can say B1 gave us 0. So now let's check B2. So we're looking at these to compose our matrix now. So B2 is equal to negative 1, 2, 5, 3 divided by 2. And so in this case, we see we have 3 minus 10, negative of that divided by 2. So we're actually not going to have a 0 value. So in this case, that ends up being 3.5. And then for this term, we get a 0. So what we see there is we do not have an entire row of zeros, and we've of course not talked about that case yet, but we want to be able to distinguish between a 0 only in the first column and an entire row of zeros. In this case, we have the former. So what that means is we're going to use either our epsilon method or our reverse coefficients method. So what we're going to do then, as defined in our epsilon method, we're going to get rid of the 0 and replace it with epsilon. And so we're just going to have this variable in our Routh table. So what we can see if we sort of do the same process to find all of the other rows of our Routh table, and I'll let you guys confirm this by working by yourself, we'll get for this entry here 6 epsilon minus 7 divided by epsilon. And so that's where we would have been divided by 0, but now it's epsilon. Here we have 3, and this ends up being 0. For this term here, we're going to have negative 3 epsilon squared plus 21 epsilon minus 24.5. And so I've kind of drawn my columns a little close, so maybe I should let me shift these over so there's no confusion about sort of columns overlapping there. The second and third entry in that row are just 0. And so I forgot my denominator here. This is going to be 6 epsilon minus 7. And then finally for our last row, we're just going to have a 3, 0, 0. And so again, we can kind of see that pattern I've mentioned before. So for instance, this 3 goes over 1, down 1, over 1. No, that's not right. Over 1, down 2. Sorry. Over 1, down 2, over 1, down 2. There we go. All right, knew there was a pattern in there somewhere. Okay, so now we have completed our Routh table using the epsilon method. So how do we analyze it from here? Well, what we want to do is we want to focus on this first column. So I'm actually just going to copy this. So we want to focus on this first column. And remember, we can let our epsilon go to 0 from the positive side or the negative side. So let me sort of, to make this more clear, let me make an actual table. And so let's say, what happens if we let our epsilon be some really small value? So it's going to 0 plus. And if it's helpful for you, you can actually look at a specific value. So maybe you want to say, let's let epsilon equal 0.1. You don't necessarily need to do that. You can just have sort of an arbitrary small value in your head. But what we're going to do is then we say, okay, well, and let me move this up a little bit. So of course this 1 in our first row or our first column here, so this 1 right here and this 2, those are going to be positive regardless of what our epsilon value is. So we're just going to say that's positive. So now if our epsilon is some small positive value, this epsilon here is also going to be positive. For our next column, however, we look at the numerator and we say we have 6 epsilon, so that's going to be a small value minus 7, so divided by epsilon. So the 6 epsilon minus 7 is something small minus 7, so relatively large. So we get a negative number over a small positive number, so that's going to give us a negative number here. So we can do the same type of thing for this next entry as well. So we could say these two terms with epsilon are going to be relatively small, this one in the denominator as well, such that we're left with approximately negative 24 divided by negative 7, which is going to be a positive number. So we'd say this is positive, and then of course the 3 down here is going to be positive regardless of our epsilon value. So we get something that looks like this. So this is where we're going to evaluate our sign changes. So from there, it's the same thing that we've done before. So we can see going from this entry to this entry, we have one sign change, and from here to here we have another sign change. So the first one is positive to negative, the second one is negative to positive. So we would say we have two sign changes, which remember means we have two poles in the two poles in the right half plane. And remember we had said this was a fifth order system right here. So we're expecting 5 poles. So if we have 2 poles in the right half plane, then that implies that our other 3 poles are in the left half plane. But again, remember, just by definition, if we have any number of poles in the right half plane, then that indicates that our system is unstable. Okay, so now just sort of to prove clearly that we could have also let our epsilon go to 0 from the negative side, we could consider some small negative value. And again, if it's helpful, you can consider some explicit value. So you could say epsilon equals negative 0.1, and you could just plug it into our equations. So of course here what we see is that for our 1 and 2 in those first 2 entries, those are going to be positive regardless. Of course, this 3 down here at the bottom is always going to be positive as well. So now our epsilon term, so our epsilon right here is just going to be the small negative value. So that's going to be a negative number. For the next entry, we have some small negative number minus a negative number, minus a positive. So we're going to have something negative in the numerator. But now we also have this negative value in the denominator. So we get negative over negative, and so that is going to be a positive value. Similar analysis for this term here. We have anything with the epsilon is essentially going to be negligible, and we still are left with just that negative 24 over our negative 24.5 over negative 7. So that is still going to be a positive value. And so even though the signs are in different places, notice that we still have 2 sign changes. So from here to here, we go from positive to negative, and from here to here, we go from negative to positive. So we still have our 2 poles in the right half plane because we have 2 sign changes, ultimately indicating that our system is unstable.